What's up, everybody? It's time for Unit 15 right now. Oh yeah, let's get this thing rocking right now. Unit 15, inverse trig functions. Yeah, all right, so let's get this going on here. All right, so inverse trig functions are exactly that. We'll get into inverse trig functions. You've talked about them already. The arc sine, the arc cosine, the arc tangent. But we're going to talk about some restrictive domains today, and we're going to make it happen. All right, so first, let's begin with what you know. Let's review. Y equals the sine of x. Looks just like this. I'm going to go pretty quickly through this. Let me use a different color pen. There we go. From 0 to 2 pi, and I'm talking about one period of each of these functions, and we're going as high as 1 and as low as -1. Oops. Okay. All right. Cosine of x looks like this, and you can make those sound effects while you are doing your homework. Your parents will think you're very cool, especially at this point in the quarantine. They're hearing you make those sound effects while you're doing your homework. They're like, something's wrong with my child. All right, and finally, let's go to y equals the tangent of x. Now, tangent of x are where we had some asymptotes at -pi/2 and at +pi/2. You know what? I just learned something too. I could use different color pens. Oh my goodness! I did not realize this beforehand. So let me make an asymptote right there. Ooh, that's an ugly asymptote. And then let's go back to the red color that we had going on right here. And tangent looks like this. There we go. All right. So now we get to the reciprocal trig functions. And the reciprocal trig functions, cosecant, the reciprocal of sine, has asymptotes at 0 and pi and 2 pi. And while I'm at it, I might as well just do this for secant. Secant's going to have asymptotes at pi/2 and 3pi/2. And cotangent will have asymptotes at 0 and pi. Okay. The reason why I'm doing all that right now is because I am now going to go to my blue pen, save myself some anguish, and I am going to draw myself some asymptotes right now at 0 and pi and 2 pi. And I'll draw an asymptote at pi/2 and 3pi/2. And then I'll draw myself asymptotes at 0 and pi. Okie dokie. Let's get to it now. Let's get it popping. All right, so unlike sine, which is basically restricted within -1 to 1 in terms of its range, cosecant begins at the peak of sine and has an upward parabola shape. Cosecant also begins at the valley of sine, which is right there, and goes downward from there. Cosine's reciprocal is secant, so a valley right there at -1. Remember here, downward parabola. And because we're only graphing one period of secant, we're starting right here at the peak and right here at the peak of cosine, and we're going inward from there. So we're starting at 1, and we are doing half a parabola opening up. Ooh, that's an ugly half a parabola. There we go. Sorry, just difficult drawing sometimes on this. And that's 2 pi, so I'll even extend it a little further. And then at 1 here, half of a parabola going up. So 2 half parabolas, although that's quite ugly right there, you get the gist. Last but not least, cotangent. I'll put pi/2 right here. And it is a graph that looks like this. Okay. Ladies and gentlemen, I present to you the 6 trig functions that you have graphed with Mrs. Middleton, or I'm going to assume you graphed with Mrs. Middleton. You have. Whether you remember it or not, that's another question. But there they all are. Huzzah. Okay, now let's go to the next section. Is y equals sine of x a function? Yeah, it is, right? It most definitely is, because it passes the vertical line test. If I draw a vertical line, vertical line, vertical line, vertical line, vertical line, it passes the vertical line test. So yes, because it passes the vertical line test, VLT, vertical line test. Is y equals sine of x a one-to-one function, though? If you recall, what does it mean to be a one-to-one function? First, it has to be a function. Second, by passing the vertical line test. Second, it has to pass something called the horizontal line test, where if I draw a horizontal line right here, and I'm going to use a different color pen, and I'll use green. It's not easy being green. All right, so if I draw a green line, does this function pass the horizontal line test? No, it doesn't. All right, so let me erase that right there. Yeah, see you later. Peace. Okay. Yeah, it doesn't pass that. So I'm going to write here. Is it a one-to-one function? No, it's not, because it doesn't pass the horizontal line test. Interestingly enough, all right, because what happens when you take the inverse of a function, everybody? When you take the inverse of a function, x becomes y and y becomes x. In other words, the domain becomes the range and the range becomes the domain. So and remember, this title is all about inverses. So in order for the inverse to be a function, not only does the original function have to be a function, but it has to be a one-to-one function. So our goal for this lesson right now is to restrict the domain of trig functions so that each inverse is also a function. All right, thus, the following trig functions that are created are not only functions, they're functions, but they're also one-to-one functions. In other words, they're going to pass the vertical and horizontal line test. So what do we do with that? All right, so I'm going to write this first off here. A capital letter. Capital letters denote that it is going to be a one-to-one function. So it's a capital S, it's a capital C for cosine, it's a capital T for tangent. That's imperative. There's a big difference between lowercase sine and uppercase s for sine. So let's look right here at uppercase sine. It's not one-to-one. But what if, and I'm going to use a moon pen for this, what if I cut off sine, say, I don't know, right here, and also continued it right there, and then cut it off right there, and I got that little sliver. Okay, and I'm going to erase that because I know on your sheet it's going to look really weird. But yes, if I did that, let's see. Remember, this, these are called periodic functions. They go forever to the left and forever to the right. So sine is going to go up, and it keeps increasing until you get to pi over 2. But then, if I continue this periodic function to the left instead of continuing it to the right, because it's going to bend down upon itself, it won't be one-to-one anymore. So what if I went to negative pi over 2? Look what I've just done. I've created a restricted graph of sine that is not only a function because it passes the vertical line test, it's also a one-to-one function because it passes the horizontal line test. So let's talk about the domain and the range of the restricted value for sine. Oh, and by the way, just so you know, for y equals the sine of x, lowercase sine of x, the domain is just all real numbers. The range goes from -1 to 1. Interesting, right? Interesting. And so the domain for this here goes is not all real numbers, but only goes from negative pi over 2 to positive pi over 2, because it needs to be 1 to 1. The range also goes from negative 1 to 1. Yeah. All right, so how about the restricted value of cosine? Well, let me start to draw a cosine. I got to stop right there. If I start to bend it back up, it's going to not be 1 to 1. So I have to stop right there. Well, what are these key values right here? This is pi over 2, and this is pi. So I draw anything more, it won't be 1 to 1 anymore. So let's talk about the domain of this restricted value for cosine. My domain is going to go just from 0 to pi. My range is still going to go from negative 1 to 1. Interesting. We are creating domains and ranges for our restricted functions. Awesome news about tangent. Absolutely nothing changes. So, sorry, I'm not going to draw a different asymptote colors this time. Nothing changes with tangent. The domain, however, though, goes from negative pi over 2 to positive pi over 2, but it doesn't touch them, so soft brackets. Negative pi over 2 to positive pi over 2 with soft brackets. And the range? Well, my friends, the range is indeed just all real numbers. Goes up and down forever, yo. All right, so you know what? Let's talk about cotangent first, because cotangent, another one where absolutely nothing changes. We got the asymptote here at 0 and at pi, and the graph's going to look like this. So my domain, soft brackets once again, goes from 0 to pi. So I'm not touching 0, I'm not touching pi, we have asymptotes there. And the range is all reals. All right, great. So now let's get to cosecant and secant. Because cosecant is the reciprocal of sine, the graph of cosecant, or the restricted graph of cosecant, is going to be based off the restricted graph of sine. So I am going to put an asymptote right here at pi over 2. Actually, it's not an asymptote, I'm sorry. Yeah, I know, I misspoke right there. Apologies. It's not an asymptote. And I'm going to put negative pi over 2 right here, because that's where the restricted graph, I'm going to use it with the cursor, that's where this restricted graph is. But I'm going to start here at the peak, and I am going to draw a half a parabola that goes up. So let's look at the original graph of cosecant. See how this graph right here goes up towards the y-axis? It's exactly what I'm going to do. So there is an asymptote for cosecant, and it's right here on the y-axis. So I'm going to start right here at 1, and I will put a dot there, and I will draw half a parabola opening up towards that graph right there. And then I'll put a dot here, negative 1, I'll put a dot right there, and I'll draw half a parabola going downward. There's my graph of cosecant, y'all. Okay. The graph of secant is based on the restricted graph of cosine, so I'm going to be putting an asymptote right here at pi over 2. And I'll put the asymptote right there. And here's positive 1, here's negative 1. I'm going to be doing half a parabola opening upward right there. And I'll go all the way out to pi. And then hits a valley right here. Restricted cosine hits a valley right there, so I'll just call it capital cosine. So I'll put a dot right there and draw a half parabola opening down. Ladies and gentlemen, dun, 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 I present to you the 6 graphs. One thing I have not done yet is I haven't done the domain and range of cosecant and secant. So let's talk about that right now. The domain of cosecant. So if you could see, I'm going from, let's just take the picture here, I'm going from negative pi over 2, and I'm going to 0 here, which is right here, but I'm not touching it, so I'll do 0 with a soft bracket. Okay, and I'm going to put the or symbol, or. I'm also starting at 0, and I'm going to pi over 2. This is crucial. This is crucial right there. Okay, and so my range, which I did not leave enough space for, I'm going to put right here. My range is going from negative infinity to 1, to negative 1, sorry, or from positive 1 to positive infinity, soft bracket. Let me try to create a little bit more space right here for secant. If I can, let's see. My domain, let's just follow the graph, is going from, this is 0 right here, so 0 to pi over 2, soft bracket, or from pi over 2 to pi. And my range is identical to the range of cosecant. So I'm going from negative infinity to negative 1, or from positive 1 up to positive infinity. If at any point you feel a little confused, rewind this video, pause it, replay certain aspects of it until you feel like you've gotten it down. All right, last but not least, let's go through this right here. I created 8 examples, one with lowercase, one with uppercase. First off, the sine of 30 degrees. Hopefully we have that down. With Miss Middleton, I don't know how you evaluated trig functions. I don't know if she made you memorize them, if she had you draw triangles. I'm going to go relatively quickly. You can email me if you have questions on these. But sine of 30 is 1/2. Restricted sine of 30, capital sine 30 I'm going to call it. Well, is 30 degrees within our range? Yes, 30 degrees is pi over 6. Is pi over 6 in this interval? It is. So, guess what? Same darn answer. Now here's where things get a little dicey. The sine of 150 degrees. Remember, the domain of regular sine is all real numbers, so I could find the sine of 150 degrees. The sine of 150 degrees is just the reference angle of 30 degrees, right? It's a 30-degree reference angle, so that's also 1/2. And because it's in quadrant 2, it is positive. Sine is positive in quadrants 1 and 2. All students take calculus. Remember that little acronym that Mrs. Middleton taught you? Now, restricted sine of 150. Does sine go into quadrant 2? It does not. It just goes from positive negative pi over 2, which is quadrant 4, and quadrant 1. So this is just quadrants 4 and 1. I know visually this looks like quadrants 1 and 3 right here, but negative pi over 2 is negative 90 degrees to positive 90 degrees. That's quadrants 1 and 4. So because 150 is in quadrant 2, this is a no solution right here. This is a no solution because it's not in the domain of sine. That is what is up right there. Okay, how about the sine of negative pi over 4? All right, so negative pi over 4, lowercase sine, that's anything, so that's what, negative 45 degrees? And it's quadrant 4, so that's negative root 2 over 2. Capital sine, negative pi over 4. Again, is that between negative, let's look at the domain of restricted sine. Our restricted domain is from negative pi over 2 to pi over 2. That's from negative 90 to positive 90. Negative 45 is definitely within that. So guess what? When it's within the domain, the answer is not different. It's the same, everybody. But I'm about to bake your noodles right now. What if I say the lowercase sine of 315? Let me draw a little line right here. 315 degrees. Hey, well, you know what? That's the same as negative pi over 4, so that's just negative root 2 over 2. Interesting. But what if I say capital sine of 315? Now listen, I know some of you are saying, well, 315, that's just 7 pi over 4. Or 7 pi over 4 is just negative pi over 4. So it should be the same answer, right? Unfortunately, no. You have to maneuver the angle in whichever direction that it tells you to go. So 315 degrees, unfortunately, has to go clockwise through quadrants 2 and 3. I know this sounds weird. I remember asking this question myself when I was in high school. You have to, I know this seems weird, but for this restricted domain, you have to go directly in the direction that the angle says. So it has to be negative to go downward. If you have to traverse through quadrants that are not within the domain, then it does not have a solution. I know that seems so weird, but yes. All right, so I'm going to put a star by that one because that is so strange, right? Okay, but if you have to go directly in the direction of the domain itself. All right, so let's finally get to cosine of 3 pi over 4. 3 pi over 4 is 135 degrees, but think about this. Is 3 pi over 4 within the domain of cosine? Yeah, you're traversing from 0 to pi. So 3 pi over 4 is within that specific domain. So basically, just the cosine of 135 degrees, which is root 2 over 2. And because it's quadrant 2, it's negative, because cosine is negative in quadrant 2. Restricted domain cosine, hey, ain't no thing but a chicken wing. It's the same exact thing. All right, so yes, I understand fully that some of you might be a little confused why this works and this doesn't, but it has to do with going directly in the direction stated. Negative pi over 4 is within this domain. 315 degrees is not within this domain. As strange as that seems, got to go with it. All right, everybody. I hope this helped. Ask questions if you got them.